in one molecule of water, you have 2 atoms of hydrogen, right? 2 atoms of hydrogen. When you have 6.022 into 10 raised to 23 molecules of water, you will have 2 times that number of hydrogen atoms. So let's put it this way. See, 1 mole of H2O water contains how many atoms of hydrogen? That is 2 times 6.022 into 10 raised power 23 atoms of hydrogen, right? That's it. Now you are given 5 moles of water. So in 5 moles of water, 5 moles of water will contain how many atoms of hydrogen? So let's see, once again the same thing, you cross multiply, x is equal to, this is 5 moles multiplied by 2 times 6.022 into 10 raised power 23 atoms of hydrogen. So the whole thing divided by, this is just 1 mole, right? So you got to write these units properly. It's very important. Mole and mole, they get cancelled. So finally, the number you're going to find is 10. 10 into this, we add 1 0 there. It is 6022. 1 more 0 here to 10 is power 23 atoms of hydrogen. The decimal point, 3 digits from the left, comes here. When you write this in scientific notation form, 6.0220 into 10 is power, it becomes 24 atoms of hydrogen. That's it. So this is how you're supposed to work out these problems. So I'll just give you 2 problems for you to work out. Let's see. The first one is find the number of the sixth one. Find the number of its molecules, right? Let's see. Okay. The first problem for you to work out is find the number of molecules of ethane, number of molecules of ethane. Formula of ethane, you know, C2H6, right? So you find the number of molecules of ethane in 10 moles of ethane. 10 moles of ethane, right? And the next question, this is question number 6, right? Question number 7 for you is number of atoms of carbon and hydrogen, right? Find the number of atoms of carbon and hydrogen in it is again let's make it 8, right? 8 moles of methane. 8 moles of methane. Alright, so you can just write out yourself. So these 2 problems you can try it on your own. And now next we are moving on to the next subtopic, that is percentage composition. Now talking about percentage composition actually gives the mass percent of every element that is present in a compound. It gives the mass percent of every element that is present in a compound. Now in fact it's very important to know the purity of compound. So in order to know the purity of a compound, we find the mass percent of each element present in a compound and then compare it with a pure sample of the compound. That is what is done. So it is percentage composition, the next subtopic. Percentage composition of compound, right? So as far as percentage composition of a compound, like it says the percentage composition of an element in a compound is given by the expression mass of that element in the compound. So let me put it this way. We take it as mass percent log of any element, right, of element is given by mass of that element in the compound. Mass of that element in the compound divided by the molar mass of the compound. Molar mass of the compound into 100. When you do this, you will get the mass percent of each element. That's it. So now we'll take up one example. The very first example is we will try to find the mass percent of the two elements hydrogen and oxygen in water. So this is H2O, right? Now, talking in terms of their atomic mass, like we know that in water you have two atoms, hydrogen it is 2, when you take these in grams it is 2 grams, then oxygen it is, each oxygen atom has an atomic mass of 16, it is 16 grams. So finally the total here is, the sum of these two is 18 grams, right? That's it. Now, since we are talking about percentage composition, we'll consider or calculate these in terms of percentage. So the percentage of hydrogen in water, percentage of oxygen in water. So let's see, the first one is mass percent of hydrogen, right? Is given by mass of that element here, it is hydrogen. So I write 2 here, 2 grams divided by the molar mass. See, the molar mass of H2O, water units, 18 grams. So it is 18 here, 2 grams, 18 grams into 100. In terms of percentage, you're going to get this as, I think it's 11.1. Yeah, it's 11.11%. And then the next thing is mass percent of oxygen, right? Again, the same thing. You take the mass of oxygen, it is 16 divided by the molar mass, it is 18. 16 grams by 18 grams into 100. This will finally give you, this is to 816 to 918, so 800 by 9. So it is finally equal to 88.89%. 88.8990, right? So it's 88.89%. So the sum of these two, it's going to be 100, right? And that's it. So this is how we find the mass percent or the percentage of each element present in a compound. So you can do the same thing for any other compound as such. So like let's take up an example here to find out the mass percentage. So the very first example I have for you is the problem here says, okay, question number 1. How much sodium, that is Na, can be extracted from it's 2 kg of sodium hydroxide. 2 kg sodium hydroxide. So this is the question. Now, sodium hydroxide. This is what is supposed to know. Sodium hydroxide. Now, in sodium hydroxide, sodium it's 23, oxygen is 16, hydrogen it's 1. The sum of these it is 40, right? 20, 30, 40, 40. If you take into grams, it is 40 grams. It's a molar mass here. Now, when you have Sodium hydroxide. The mass percent of sodium in sodium hydroxide, that is in terms of 100. So when you have 100 grams of this thing, then the mass of sodium alone in terms of percentages, mass percentage of sodium is 23 divided by 40 into 100. And here you are getting something like my value here, it is 57.5%. And that of oxygen, right? Mass percent of oxygen, it is again 16, yes, 16 by 40 into 100. And the value here happens to be for oxygen, right? I have to do the calculation right this way. And then 16, 14 to 40, I think it's 40% here. And then mass percentage of hydrogen, it is just 1 upon 40 into 100, right? So it's like this. So 10 divided by 4, 2 to the 4, 2, 5 to 10, it is 2.5%. And here you can see that in terms of percentage, mass percent of sodium is 57.5, that of oxygen is 40, and that of hydrogen is 2.5. When you add up these, the sum should give you exactly 100%, right? So now the question is, how much sodium can be extracted from 2 kilogram or 2 kg of sodium hydroxide? Now this 2 kg of sodium hydroxide should be converted into grams, into grams. Now when you have 100 grams, the sum of these, that is this one and this one together, it's 100%, right? It's 100%. So when you have 100 grams, the mass of sodium is 57.5%. And when you have this 2 kg becomes 2000 grams, right? So now what we do is, see, 100 grams of sodium hydroxide contains, okay, it is 57.5%, right? 57.5 grams of sodium. Now this 2000 kilograms nothing but, 2 kilograms nothing but, and 2000 grams of sodium hydroxide contains, okay, let's take it as x, again the same thing, you cross multiply, x is equal to, this is 2000 grams into, there you have 57.5 grams, the whole thing divided by that is sodium, 100 grams of sodium hydroxide. These two get cancelled, 2 zeros from here, 2 zeros from here, and when you multiply these, okay, 1 0 here, then 2 5 10, 14 15, alright, let's see, 0 2 5 10, 1 remains, 2 7 14, 5 2 10 11, alright, once again, okay, 2 5 10, 14 15, 10 11, great. So the decimal point is on here. It is in terms of grams. When you write this in kilograms, it becomes, you divide this by 1000, it is 1.150 kg. So this is the amount of sodium that can be extracted from 2 kilogram of or 2 kg of sodium hydroxide. That's it. So this is how you can do these calculations based on percentage composition. So I'll give you one problem to work out. Let's say you just apply the same rule, and the question here is, right, question number 2, how much sulfur can be extracted from? How much sulfur can be extracted from, let's see, 10 kilogram of, this is sodium sulfate. The formula of sodium sulfate is Na2SO4. And I should tell you that the atomic mass of sulfur is 32 unified mass, right? Or you can take it as 32 grams. For sodium, you know it's 23, and oxygen, each oxygen atom is 16. And this is how now you will work out these problems on percentage composition, and the same thing can be done if you're given any other compound. That's it. And now next we will move on to the next part, is empirical formula and molecular formula. Okay, so the next thing is about empirical formula and molecular formula. Now, talking about molecular formula, the molecular formula of a compound represents the exact number of atoms of different elements present in a molecule of the compound. So it shows, or it represents the exact number of atoms of different elements that are present in a molecule of the compound. Now, the best example is like, for example, if you write C2H6, this is ethane, isn't it? So this is the molecular formula of ethane, and you know that in a molecule of ethane you have 2 atoms of carbon and 6 atoms of hydrogen. So this is the molecular formula of ethane. Likewise, if you take up C6H12O6, this is again the formula of glucose, and here you have 6 atoms of carbon, 12 atoms of hydrogen and 6 atoms of oxygen. So this is the molecular formula of say glucose. And likewise, you can go on writing, like suppose you have C2H2O4. This is again the molecular formula of oxalic acid, or this is ethane dioic acid. Now, these are called molecular formulas. If you write H2O, again this is the molecular formula of water. Now, here you see that these formulas, they represent the exact number of atoms of different elements that are present in a molecule of the compound. Now, as far as empirical formula is concerned, empirical formula, an empirical formula represents or shows the simplest whole number ratio of the various atoms that are present in the compound. So, say in a molecule of the compound. Now, here, as far as the molecular formula of ethane is concerned, it is C2H6. Now, the empirical formula of this compound, that is ethane, C2H6, will be your C2H6. This is 2 1s, 2 3s. So it becomes CH3. Now, this is CH3. So there is C1s, there is 1C and then 3H. So CH3, it is the empirical formula of ethane. There in the ratio 1:3. Likewise, the empirical formula of glucose will be, so this is 6 1s, 6 2s, and 6 1s, right? Or CH2O. CH2O. It is the empirical formula of glucose. And next, again, here it will be 2 1s, 2 1s, 2 2s, 4. So it is CHO2. This is the empirical formula of your compound, that is oxalic acid. Likewise, we can have many such examples. So that's the meaning of these two, that is molecular formula and the empirical formula. Now, the next thing we're going to take up is determination of empirical formula and molecular formula of a compound. So the thing is, when you are given the mass percent of the various elements present in a compound, then you can determine the empirical formula of the compound. So to determine the empirical formula of a compound, in fact, you will be given the mass percent of the various elements that are present in the compound. So using this mass percent of the various elements present in a compound, you can find or you can determine the empirical formula. And again, the other thing is you can also find the molecular formula of a compound using this empirical formula. So the molecular formula of a compound is given by multiplying the empirical formula. After you have obtained the empirical formula, when you multiply it by n, then you will get the molecular formula of the compound. And you may wonder what this n is, small letter n here. N is obtained by dividing the molecular mass or the molar mass of that compound by the empirical formula mass. So you will see it here. I have an example for you, and based on this, you can learn how to find the empirical formula and the molecular formula. So the first thing is we're going to work out one problem here to find out the empirical formula of the compound, right? So it says a compound contains 75% carbon and 25% hydrogen. Now you are asked to determine the empirical formula of the compound. Empirical formula of the compound. Now there are certain rules here, and I've just shortened the whole thing, and it's become very simple now. You should know how to write this tabular column here. Based on this, you can easily get the empirical formula. So let's see. In the very first column, you see the heading here is elements. Next, you will write the mass percent. Now it's important that the mass percent of the elements that are given in the problem should be changed into grams, right? Mass percent, you sort of convert it into grams, because you're going to take the molar mass of the elements, molar mass of the elements, and then when you have it in grams, you will get the number of moles of each element, and then you can finally go to the simplest ratio of atoms. So here the elements are, compound contains 75% carbon, so element here is carbon, you will see here. And mass percent is 75%, now in terms of grams, as I said, is 75 grams. And then the molar mass of carbon, it's 12 grams actually. You write 12 here. Number of moles of carbon here, it is mass in grams divided by molar mass is 75 by 12. Let's see, you get some number here. You got a good calculation. The next one is hydrogen. It is 25%, so it is 25 grams. And you know that the molar mass of hydrogen, that is actually, if you know the atomic mass of hydrogen, it is 1. When you express in terms of grams, it becomes the molar mass. And then number of moles here, it is 25 divided by 1, it is 25 itself. And there, when you divide 75 by 12, let me do it faster. Here you're getting, it is 6.25. 6.25, right? Now the next step is to find the simplest ratio of atoms. It is 0, right? It's 25 and 0, there's nothing here. So now, number of moles, this is 6.25, this is 25 moles of hydrogen. Now, here to get the simplest ratio of atoms, what we do is, we look for the smallest number of moles here. Out of these, this is 6.25, this is 25. And now 6.25 is lesser than 25. So you divide each of these, that is number of moles, by the smallest number. This is 6.25 divided by 6.25 is 1 itself. And again, this 25, you're going to divide it by 6.25. So 25 when divided by 6.25, you're getting 6 plus 12, it is 4, right? 4. If I'm not wrong, that is 4. So now the simplest ratio of atoms, that is, you're getting 1 here for carbon and you're getting 4 here for hydrogen. So now you write the empirical formula, that is, therefore the empirical formula of the compound, empirical formula of the compound is it is 1, and hydrogen it is 4. It is CH4. So this is now the empirical formula of the compound. In fact, this is methane, right? It's already in the simplest whole number ratio. So this is the empirical formula as well as the molecular formula of compound methane. So that's how you can find the empirical formula of a compound. Now, knowing these steps well, you can easily work out any problem of the same type. So we'll take up another example here to find the empirical formula and also the molecular formula. So the next problem I have here for you is, let's see, question number 2. It says a compound contains, it contains 82 point, we're going to take it as 82.8% of carbon. Then it is just 2 elements on the right. Oh, 82.8% carbon and 17.2. Let's make 7.2% hydrogen. Now you have to determine or find the molecular formula. Find the molecular formula of the compound if its molar mass or molecular mass is 58 AMU. Now, if you take it as AMU, it becomes the molecular mass. If you take it in terms of grams, it becomes your molar mass of the compound. So, the answer or your solution here, right? You will write element here, then you write the mass percent, that is in grams. Then you have the molar mass of the elements, and then the next is number of moles, and finally it is the simplest ratio of atoms. Simplest ratio of atoms. Okay, that's it. So you have just 2 elements, the first one carbon and then hydrogen. To find the molecular formula, you have to first find the empirical formula. Once you have found the empirical formula, then you will find the molecular formula by multiplying it by N. See, carbon here it is 82.8 and hydrogen it is 17.2. The sum of these two should be 100. The molar mass here of carbon units 12 and that of hydrogen is 1. So this is 82.8 divided by 12. You get some number here, and this is 17.2 divided by 17.2 divided by 1 is 17.2 itself. Here when you divide, you are getting, my value here is 6.9. Yeah, 12, 672 or 6 point, you take this 9. You're going to take this as 17.2. Fine. Now the next thing is to get the simplest ratio of atoms. You're going to divide both these numbers, that is number of moles, by the smallest number of moles. 6.9 is lesser than this. So 6.9 divided by 6.9 is 1. 17.2 divided by 6.9. 6 2 is 12. 6 3 is 18, 7, so it's 2.5, almost 1. You're getting 2.5 here. Now, the simplest ratio of atoms here, for carbon you're getting 1, for hydrogen you're getting 2.5. Now, here to Write the empirical formula. In fact, the definition says, empirical formula, it actually shows or represents the simplest whole number ratio of the various atoms present in a compound. So this is not a whole number as such. So what happens is, to write this in the simplest whole number ratio, you're going to multiply this by 2. If you multiply this by 2, you will also multiply this by 2. So it's going to become 1, 2, 2. 2.5 2 is 5, right? So these two, that is for carbon it is 2 and for hydrogen it is 5. So now your empirical formula. So the empirical formula of the compound is, C, it is 2 here, and for hydrogen you are getting 5, C2H5. Now to write the molecular formula, you have to find the value of N, and the value of N, as you know, is given by the molecular mass divided by the empirical formula mass, right? So I've got it 58 by 29, yeah. So here the molecular mass, that is 58, divided by the empirical formula mass. Your empirical formula is C2H5. Now here you have 2 atoms of carbon. Each carbon is 12. So 12 into 2 times, plus each hydrogen is 1 into 5. So it is 12 to 24 plus 5 is 29. So now the empirical formula mass is 29. Okay, 29 here. So 29, 2 times you get 58. So your N is 2. Therefore, the molecular formula of the compound is N times, right? N times C2H5. When I say N times, you're going to multiply this 2 by N. Your N here is 2. 2 C2H5, it is C4H10. This finally becomes the molecular formula of the compound, right? Molecular formula. This is your empirical formula. And this 29, it is your empirical formula mass. And the value of N, as you can see here, can be obtained by dividing the molecular mass or the molar mass by the empirical formula mass, right? So we're taking the molecular mass means 58 AMU by the empirical formula mass, it's 29, you're getting 2 here. So that's it. So this is the molecular formula of the compound. So you'll have to do the same thing for the remaining or rest of the problems of the same type. So now I'll give you one problem to work out. You can try it out on your own. So let's see. Question number 3. So here you're going to have next one. A compound is found to contain 26.7% carbon, 2.2% hydrogen, and 71.1% oxygen. Now find you just find its empirical formula. Find its empirical formula. Find its empirical formula. You just find the empirical formula. And another problem for you, the fourth one, here you will just find only you will find the molecular formula. For the next one, you will find the molecular formula. This third problem is simple because you just have to find the empirical formula. Only the fourth one now, it is, I put it this way, a compound contains, okay, 40% carbon, 6.7% hydrogen, and 53.3% oxygen. Now find the molecular formula of the compound if its molecular mass is 180 AMU, or 180, you can also write U, that is unified mass. So you try to work out these two problems on your own. I think you have understood how to do it. So with this I'm going to stop my lesson here. Thank you very much. Thank you.